So today we will start talking about pulse width modulation and how it is used to control the servo motor. Now, servo motor is a special type of motors. These motors are controlled basically by varying the angle. Okay, they are controlled by varying the the duty cycle at a certain frequency. What we started on last time was talking about how to control the microcontroller, how to generate a pulse width modulated signal using the microcontroller. Now, in terms of frequency, the only way for us to control the frequency was to use the prescalers, okay, for the original microcontroller. So if my microcontroller is running 1 megahertz, what I can generate over here is 1 megahertz divided by 8, or 1 megahertz divided by 64, or 1. Yes. Sorry, I'm not sharing, no problem. So again, once more, what we can generate is the 1 megahertz divided by 8, 1 megahertz divided by 64, since over here, and 1 megahertz divided by 256, and finally the 1 megahertz divided by 1024. So this will give us a value of can do it very fast, which is 1/8. This one is 125 kilo, and 64 will give us 15.6 kilo, divided by 256 will give us around 4 kilo, and divided by 1024 will give us around 1 kilohertz. Now, this is good, this is fine, but assume that you want a certain frequency. How can you get a certain frequency? Since here we are limited to these values. If we have 1 megahertz, we can get only the divisions of the 1 megahertz. Either the 1 megahertz, the 1 megahertz divided by 8, the 1 megahertz divided by 64, or the 1 megahertz divided by 256, and finally the 1 megahertz divided by 1024. Sorry. So how can we get the different frequencies? In order to do that, an application for that also is the servo motors. The servo motors, if you did not see them, they are small blue motors. They look something like this. Okay, and these motors, they have 3 wires. Okay, these motors, they have 3 wires. They have a lot of applications, and they operate basically in robotics. Most of the robotics, they use these servo motors, not this brand, but the same idea. So a servo motor is an electrical device for precise control of angular rotation. Precise control of angular rotation. The servo motor can be controlled to move in angles. So when you move in angles, it's very useful for robotics. It's very useful for opening and closing valves. It has a lot of applications. So it is used where a precise control is required, like the case of control of a robotic arm. It consists of a suitable motor with control circuitry for precise precision and control motor shaft. It is a closed loop system. The rotation angle of the servo motor is controlled by the pulse width modulation. This motor is different. This motor requires no driver. This motor, you will just give it 5 volts from the source and ground, connected to ground, and then you just vary a pulse width modulated signal at a certain frequency. Okay, it's a little bit different than the other motors we are using. So by varying the width of the pulse width modulated signal, we can change the rotation angle and the direction of the motor. For more information of the servo motor, refer to the servo motor topics and servers in this section. Now look, over here we have a PDF I uploaded for you, which is, or the link for the datasheet for the SG90. It's a 9 gram micro servo motor, a 9 gram micro servo motor. So the servo motor is considered in this case the SG90. Now this servo motor, its weight is 9 gram. The dimensions, its torque is 1.8 kilogram force per dot centimeters. The operation speed is 1.1 seconds per 60 degrees. The operation voltage is around 5 volts. The dead bandwidth is 10 microsecond, and this is the ranging temperature. Now these servo motors, they are very useful. They have very good torque, okay, very good torque, and their speed is moderate. I cannot say it's very fast, but it's moderate speed. But they operate in certain frequencies. Yani you want it to rotate 90 degrees, it will rotate 90 degrees and only 90 degrees, and it will go back to zero as you program it. Now, it has three wires. The red wire is the VCC, the brown wire is the ground, the orange wire is the pulse width modulated signal. So this one will be connected to VCC 5 volts, and this one will be connected to the ground, and this wire will go to your microcontroller. Okay, now this is how it's done. It should be running 50 hertz. It should be running a 50 hertz, which is around 20 milliseconds, and the duty cycle can be controlled, or the duty cycle will control the position. For position 0 or angle 0, the pulse is 1.5 millisecond out of what? Out of the 20 milliseconds. For 90, it should be 2 millisecond pulse. And for minus 90, it should be around 1 millisecond pulse. So you can rotate it 90 and plus 90. So the SG motor, the SG90, servo motor, practical duty cycle is from minus 90 to plus 90. So it will be either here on 0, or it will go plus 90, or it will go minus 90 down here. So it's either plus 90 or minus 90, or at 0 location. So you can rotate it in any type you want. So for minus 90, you will require around 0.52 milliseconds duty cycle. For 1.4 milliseconds duty cycle, we get a 0, and for 2.4 milliseconds duty cycle, we get the around plus 90. So how do we do this? How do we do this? Now, to control the servo motor in between minus 90 and plus 90 rotation, we need to generate a pulse width modulated signal that has a frequency of 50 Hz with a duty cycle variation from 0.5 to 2.4 milliseconds. We can generate it using the Atmega16 timer 1. Now, the reason for choosing timer 1, timer 0 and timer 2 are 8 bits, and it's quite difficult to generate large frequencies. This is a small frequencies, sorry, using this timer, because small frequency means more time. More time means more counting up. So here we are generating the pulse width modulation signal at PD5, which is output counter 1A of the Atmega16. Remember, the timer 1 will have two outputs, which is output counter 1A and the output counter 1B. So we will be using the 1A output. Here we are using 14th waveform generation mode of the timer 1 in the Atmega16. The top value of timer 1 is decided by ICR1. So we have the, let me start the whiteboard here. So we have before that, we have the modes here. No, let me go to the Atmega16 datasheet and show you the wave generation mode that we plan to use. So the Atmega16, here is the datasheet for the Atmega16. Immediately once the datasheet opens, I am going to go to where is it? Okay, I'm going to go to timer counter 1. So here, I will go to timers and counters, counter 1 here, and inside it I will go to modes of operation. So here are the modes of operation, and then I will be checking how to generate the different modes of operation or different signals. Okay, these are the modes of operation I'm talking about. This is the wave generation mode. Okay, so this is just like a table having all the information. This is this timer counter or timer 1 in the Atmega16 is more different than the previous one we studied, because it has 4 bits of wave generation mode. 4 bits 2 to the power 4 is 16, so it will give you 16 different modes. So what we are going to use is mode number 14. In mode number 14, which is 1110, we are going to use the fast pulse width modulation. Top is ICR1. Top means ICR1 means my timer counter. Okay, my timer counter will count, instead of counting from 0 to max, and max over here is 0xFFFF or 2 to the power 16 minus 1. Okay, it will be counting to ICR1. Now ICR1 will be considered our new max. So this ICR1 will be used to control the frequency. So we will be using the ICR1 in the Atmega. Okay, we are going to use the wave generation mode 14, which is a fast pulse width modulated signal, with the ICR1 as top, and the OCR1 is our bottom, and we will have the overflow also on top. So we will have the top, the interrupt flag on top, and the ICR1 as our bottom. So it's quite straightforward. I will show you how to do it and explain it through the details over here. So we will have our top value of timer 1 is decided by ICR1. ايش يعني top? يعني the counter will count from 0 to top. Once it reaches top, it will go down and start counting from 0 to top once more. The timer counter will not count to max. Max is for counter 1 65,535. Okay, but the top, it's a value that we are going to use, where timer 1 overflow will occur at timer 1 gets the value when it reaches the top. Now we use the internal 8 megahertz frequency. So what we are planning to do is basically, let me clear this one over here. Okay, so what we are going to use is, we want to generate a signal, okay, that has the frequency we want is 50 hertz. This is our output. We are going to use, طبعا the duty cycle is depending on the angle. So it depends on the angle, we will choose the duty cycle. Now our input is the 8 megahertz divided by a prescaler. Now here in the example, the prescaler is 64. So the prescaler, once the prescaler is decided as 64, so the input is 8 megahertz divided by 64, which will give us 125 kilohertz. 125 kilohertz. So what we want to do is the timer will count from 0 up to 65,535,000, and if it counts from here to here at a rate of 125, we are going to reach to a certain time. We want to find ICR1. Now to find ICR1, there is an equation. To find ICR1, there is an equation. So the fast pulse width modulated frequency, which is the frequency that we want, is equal to the frequency of the microcontroller divided by n, where n is our prescaler, 1 plus top. Okay, 1 plus top. So we know, or we don't know what is the top, but we know what is the frequency that we want. Here, since n is either 1, 8, 64, 256 or 128, and we want the 50 hertz to be our output, we will find the top, which is this value. So in other words, okay, I'm going to show you here. So in other words, what we are going to do is basically the equation is saying the the frequency of the pulse width modulation is equal to the frequency of the oscillator, f of the oscillator, divided by n multiplied by n multiplied by 1 plus top, divided by n multiplied by 1 plus top. What we know? We know that this is 50 hertz, okay, and the frequency of the oscillator is equal to 8 multiplied by 10 to the power 6, which is 8 megahertz, divided by n, which is 64. We chose n as 64, multiplied by 1 plus top. So all we have to do is find the value of top. To find the value of top, we can say, okay, let me go through the steps. It is 64 multiplied by 50 divided by 8 multiplied by 10 to the power 6 is equal to 1 over 1 plus top. Flip everything. Once I flip everything, I will get 1 plus top is equal to 8 multiplied by 10 to the power 6 divided by 50 multiplied by 64. I will send the 1 over here, so I will have like this, and then I will minus 1. So this is the value of top. Now the value of top, if you use the calculator, it will give you 2499. Okay, the value of top, it will equal to 2500 minus 1, which is equal to 2499. Now what does this mean? This means that over here my ICR1 will equal to 2499. So my counter will count from 0 up to 2499. It will go down to 0, then it will go from 0 up to 2499, and so on. Now what happens here is I generated a signal, okay? I generated a signal which is a pulse with which has a frequency of 50 hertz. Here for f is equal to 50 hertz. So this is the frequency for 50 hertz. We generated a signal for 50 hertz. The next step is to zoom in a little bit. Oops, sorry. I'm going to zoom in a little bit and talk over here that this is my signal. My signal will count from 0 up to 2499. Now I want to generate the duty cycle. In order to generate the duty cycle, I need to flip the signal inside here, because as it is, okay, as it is, my output will be looking something like this. Now, the next step is to find the value that I need to put here so to satisfy my duty cycle. And in order to do that, continue with the example. In order to do that, I need to put a value on the output compare register 1. Now, so here we know that the 2499 is used to generate the 50 hertz. Timer 1, so as timer 1 of clock it has 125 kilohertz, we get 8 microseconds per period. يعني what we mean to say is timer 1, okay, I will go here. Timer 1, from this information over here, let me zoom back here. So my timer 1 is having a frequency of 125 kilohertz, or a time period of what? Of 8 microseconds. طيب 8 microseconds. My motor will be running what? Will be running times. So if I want to generate 0.5 milliseconds, in order to control the servo motor. So the 0.5 milliseconds, how many? Okay, so I will go back once more here. To generate 5 milliseconds, I need 5 milliseconds divided by 8 microseconds counts. So this will equal to 5,000 divided by 8, and your 5,000 divided by 8, so 5,000 divided by 8 is 625 counts. I need 625 counts. Now these 625 counts, I will be putting them over here. 625, which is my OCR1, output compare register. This is my ICR1, this is my OCR1. Now what happens is, the signal will go down, then will go up, then will go down, then will go up, then will go down, then will go up, and so on. So the signal now has a frequency of 50 hertz and a duty cycle of 0.5 milliseconds over the total period of 2 milliseconds. Okay, so this is what we need to do. So in order to configure the microcontroller, you need to do two things. The first thing, configure ICR1 to generate the needed frequency, and configure OCR1 to generate the duty cycle. So these are the two steps. So this is the connection that we use to control the servo motor. It's quite a simple connection. Now let's program the AVR60 to generate 50 Hz pulse width modulated signal to control the servo motor at an angle between 90 and minus 90 and plus 90 rotation. So for the SG90 micro servo motor, here we get particularly minus 90 at 0.52 milliseconds duty cycle and 50 Hertz. So we generate and we will get that the OCR will equal to 65, where angle 0 will be at 1.4 milliseconds, and we find OCR 175, and the plus 90 is at 2.4, and OCR will be equal to 300 milliseconds. طبعا these numbers do change depending on the frequency that we use for the microcontroller. So here the microcontroller is using 8 million hertz or 8 megahertz. Our prescaler is used 64. So we get our values as ICR1 is equal to 2499 for our top. Then we set the wave generation mode into mode 14, fast pulse width modulation, with top in ICR and clear at OC1A. So this mode, once more, you can get it straightforward from over here. Okay, so we get the mode from these values over here, which is mode number 14, where top is at ICR1, and we update ICR1 as bottom once we reach to the top. So that's quite straightforward. So we get WGM13, WGM12, WGM11, and WGM10 for the settings of the microcontroller. Then we set the positions based on the calculations: 65, 175, and 300. Okay, so this is how you control the servo motor and the calculations involved in doing the servo motor calculations. Okay, so once more over here, I will go through it once more. You do the calculations based on the values that you have. So here you see I put 5 milliseconds, but in the example we wanted 0.5 milliseconds and 175 and 0.5, 1.4, and 2.4. So depending on the question, you will change the values of the OCR, which is quite straightforward. Once you get that, once you find that the frequency that you are using, let's say 8 megahertz divided by 64 is 125 kilohertz, 1 over that number will give you 8 micro, and then you choose the time that you want. If you want 0.5, you do 0.5 milliseconds over 8 micro, you will get around 65 or 62.5 counts, and so on, and you put it on the OCR. So then you just need, by simply doing the program, you can rotate the servo motor, as you can see over here. Do you have any questions on this part? Are there any questions? No questions? Okay. So I will stop here. Remember, tomorrow we will have our test at 6 p.m. till 7 p.m. Inshallah, everything will go fine. We will have our lab at 8, inshallah, tomorrow morning. Thank you.